Hello everyone, thank you for the invitation from the University of Chicago. My report is about how to summarize and extract knowledge from the shape dataset of cultural heritage. I will introduce the work from following 5 parts. And first, I will introduce the background of this research. And then I will briefly introduce some core concepts of Gaussian process and deformation fields. In the third part, I will introduce some research details such as data processing and model construction. In the fourth part, I will show you some visualization application based on our model. Finally, a brief conclusion will be given. And this is the core members of our research center. As introduced in previous report, with the support of Cyrus Tang Foundation, our research team have been working hard to build an academic platform in recent years. That is the digital art project of Chinese art in the diaspora. And we jointly work with related universities and museums to carry out a large number of cultural heritage restoration projects, such as the virtual restoration project of Binyang Central Cave of Longmen Grottos, and the digital project of Zhihua Temple, the virtual restoration of 6 states in Zhao Mausoleum of Tang Dynasty, and the digital restoration project of Xiangtangshan. With the increasing amount of data, we start to concentrate the overall information characteristics of the data. If we have enough 3D shape data, it is possible to discard the shape feature or aesthetic style problem in statistic point of view. Quantitative analysis of artwork becomes a hot research point in recent years. And digital technology not only make the quantitative comparison possible, but also provide us a flexible tool to visualize the abstract knowledge and concept. But how can we actually achieve this goal in practice? Here, we proposed a statistical method inspired by the 3D morphable model provided in the field of face recognition. In this part, I will introduce you the core concepts and method for this research. Firstly, I will talk about the representation of shapes and the concept of deformation field, which are the premise to make shape comparison possible in our research. Secondly, I will briefly introduce the core concept of Gaussian distribution and Gaussian process, which we use to describe the shape distribution of our dataset. Finally, we will introduce how to use linear algebra tools to help us to extract the main deformation modes from the shape dataset. 3D shape plays an important role in the digital research of cultural heritage. How to represent a 3D shape is a basic problem in various digital technique scenarios. Here, we use the triangle mesh to represent the appearance of the Buddha head shape. Generally speaking, a complete triangle mesh files includes vertices, triangles, and UV information. However, the shape information was uniquely determined by vertices information. So we connected and flattened the 3D coordinates of the mesh vertices in a uniform order to represent the shape as a one-dimensional vector. Based on the 3D shape representation method, we further defined the 3D shape deformation field as a difference of 2 shapes. During this process, a shape was specified as a reference. If we regard the deformation as a function defined on the reference shape, the target shape can be described as the addition of reference shape and a deformation function defined on it, which is the object that the Gaussian process was going to model. An implicit condition was that all of the shapes here should be comparable. In other words, they should share the similar shape structure or come from the same shape classes. This picture dynamically demonstrates the deformation field between two Buddhism sculpture 3D shapes. A challenging problem during the deformation field calculation is how can we define the dense correspondence of two shapes. I will introduce our method in the later section of this report. The so-called Gaussian process is the extension of multi-dimensional Gaussian distribution under the situation of continuous domain. Gaussian distribution exists widely in our daily life. I will not discuss too much mathematical concepts here, but just give you an intuitive impression of the probability distribution. Gaussian distribution is a kind of model describes the possibility of data appearing in different positions in the data space. For example, the length distribution of petals approximately obeys the one-dimensional Gaussian distribution model, while the position distribution of dart on the target plane approximately show a two-dimensional Gaussian distribution. And the Gaussian distribution tells us that the data generally scattered around the mean vector and 95% of the data are basically concentrated within two standard deviations. The expression of Gaussian distribution is concise and elegant. What's more, it has a closed form both in conditioning and marginalization operation, which make the calculation simple and efficient. The basic statistic method told us that to construct Gaussian distribution, mean vector and covariance matrix need to be evaluated from training dataset. Given the registered dataset, we can solve this using the following formula. When we want to describe the continuous 3D shape distribution, we need to use Gaussian process. For the programming, we realize the definition of Gaussian process by interpolation algorithms. Because we use one-dimensional vector to represent shapes, it brings two problems for modeling. First of all, the dataset has an ultra-high dimension. Secondly, there are obvious correlations between adjacent portions, which always show high similarity in 3D position, and this will cause seriously redundant calculation in shape analysis. The way to solve the above two problems is to find the direction where the data changes the most in shape space. If we want to measure the difference of two samples, we firstly find the direction with the largest variation, and then compare their projections on it. Principal component analysis is an efficient algorithm to find the directions in data space and reduce the dimension by data projection. The main concept it extracted here reveals the key deformation patterns of the shape dataset. In this part, I will introduce some details of our method from following sections, including the shape dataset of Buddha statue head, the registration and rigid alignment methods, and the implementation process of principal component analysis. This figure shows the main structure of our dataset. We have a total of 190 samples of Buddhist statue, including 120 samples of Buddha statue heads. From the perspective of creating regions, most of them came from East Asia, followed by South Asia and Central Asia. In terms of creation methods, the majority of the 3D data will come from photogrammetry. Although the resolution and quality of photogrammetry is much lower than the laser scanning, it is sufficient for the research requirements we conducted here. Although we tried our best to collect data comprehensively as much as possible, the data still shows an imbalanced structure. Then let's have a look at how to achieve segmentic consistency. We said that two shapes in segmentic consistency or in dense correspondence, that is, they have the same topology structure and the corresponding mesh vertices laid on the same structure position of the shape. The process to achieve this goal is called shape registration in computer graphics. The left picture shows the unregistered 3D data. Obviously, we can see that their topology structure is completely different. So the computer cannot directly measure their shape difference on the original scanned 3D data. 3D shapes registration is still a challenging task for computer vision science, even in the well-studied field of face recognition. Here, we provide a hybrid method for Buddha's head shape registration, involving shape wrapping and interactive modification. And first, we manually designed a standard 3D shape as a reference shape related to a median shape. We define this mesh as the template mesh. Then, we use Wrap4D to wrap the template mesh to the original 3D data. This is a very tedious process because we need to identify 65 key points corresponding with the landmarks on the template mesh manually. If the target shape varies too far from the template mesh, Wrap4D will cause over distortion in the process of wrapping. To solve this problem, a set of iterative brush tools have been used to release the creased and overlapped distortion. The right animation shows the shape wrapping process from the template to scanning data. And this is the registration result of 3 samples selected from our dataset. As we can see, they have the same mesh topology and the vertex order. Their similar mesh topology structure make each dimension of the shape vector inconsistent with each other. Although the registered shape were in segmentic consistency, their position, orientation, and shape were often determined by scanning strategy and conducted details. Deformation fields directly extracted under this situation will mix the shape information and disturbing transformation together. The process to remove the transformation is called the rigid alignment, and this can be solved by iterative closest algorithms. And the portion to construct closest point pairs for ICP algorithms should be focused more on respected stable locations. The blue parts on the left figure show the areas with small shapes variations evaluated by Coates method, We emphasize the weight of this portion during the rigid alignment process, and the alignment process shown on the right animation. Principal components analysis plays an important role in data dimension reduction. In addition, by principal component analysis, we can also find out the main deformation pattern of overall dataset from a statistic point of view. To conduct PCA calculation, we need to organize the shape vector into a matrix form, then calculate the mean vector and covariance matrix of the following formula. Eigenvectors of this covariance matrix is the principal components we want. And this calculation of principal components employed the same mathematical skills with Pentland, as the dimension of our covariance matrix is very huge. In the third part, I want to show you some visualization exploration of our Gaussian process model. I separated this part into 4 sections. The first one is the visualization of the mean function of Gaussian process. Secondly, the visualization of principal components of Gaussian process. Third, the ability to generate new Buddha shapes based on our models. And the last subsection is extension application on how to use the conditional rule of Gaussian process to infer the missing parts of damaged shapes. For a Gaussian process, the average function describes the overall distribution center of the dataset. We can observe that with the increase of improved samples, the mean shape gradually converged to a stable state. And the finally stabilized mean shape reflects some general features of the Buddha head. There is reasons to believe that the mean shape will update with the increase of new registered samples in the future. Now, let's have a look at the visualization of principal components. This is a visualization of the first 2 components. We arranged the eigenvectors with the descent order of eigenvalues. The figure below shows the shape deformation models represented by the first 2 principal components. Generally speaking, the top principal components controls global shapes deformation mode, such as the width and height ratio. With the decreasing of eigenvalues, the corresponding eigenvector shows more localized deformation features. And this is a visualization of the corresponding deformation in the 3rd and 4th principal components directions. By weighted linear combination of these principal components, we can generate new Buddha shapes manually or randomly. The ability to generate new data is another feature of Gaussian process model. Mathematically speaking, the generation of a new data shape is actually the result of linear combination of shapes in the training dataset. All the 3D Buddha shapes rendered here were generated by random sampling on our model, and it can be found that the majority of them were inconsistent with characteristics of Buddha statue in our dataset. While the application of missing parts inference task takes full advantage of the correlation information learned from the training dataset. The core idea is using Bayesian theory as the observations to update the prior distribution. In the damaged parts restoration scenario, residual portion can be regarded as the inputs of observations. For multi-dimensional Gaussian distribution, the inference process can be defined as the conditioning calculation on the left. To evaluate the performance of damaged parts reconstruction, we manually remove the left eye of a complete Buddha head shape. The center figure shows that the reconstruction results by our methods, and we can find that the result is acceptable both in deviation check test and visual sense. Finally, this is a brief conclusion of my report. At least I think both of the mean function and the principal component and covariance function give us new information from a statistical point of view. What I want to emphasize is that we employed various of software, computer tools, mathematical skills to construct an abstract probability model. So how can we benefit from this process, and is it worthwhile to do so? I hope the visualization of the presentation can provide you something new about the above questions. And that's all the information I want to talk about. Thanks for your listening.